Earth Systems 3209, Unit 2, Historical Geology. Text references can be found in Chapter 6, Chapter 8, Appendix A, and Appendix B. Unit 2, Topic 2.2. This topic focuses on the principles and laws used to establish relative time. Throughout the lesson, we will focus on describing the various principles and demonstrating their use in relative dating. For example, we will describe superposition, cross-cutting relationships, amongst others. When finding relative time, geologists usually use a series of relative dating principles. These relative dating principles include the law of superposition, the principle of original horizontality, the principle of cross-cutting relationships, the principle of inclusions, and unconformities. When we look at unconformities, we will focus on three different types of unconformities. One being an angular unconformity, number two being a disconformity, and number three being a nonconformity. All of these relative dating principles are used to arrange geologic events in relative time. References can be found in the text on page 218 to 223. Let's look at the first law, the law of superposition. The law of superposition states that in any undisturbed sequence of sedimentary rock, a sedimentary layer is older than the layers above it and younger than the layers below it. So if we refer to this diagram, we will notice that the layer here outlined in purple is relatively older than the brown layer, which is older than the next layer up, and so on until we get to the very top layer, which is the youngest. So as we go from the base of the layer up to the top, we see rocks getting older to rocks becoming younger. When we look at the second geological principle, the principle of original horizontality, this principle states that most layers of rock, sedimentary rock, are deposited in horizontal positions originally. If a rock layer is folded or inclined, then the layers must have been moved into that position by crustal disturbances. As we see in the diagram below, all of the rock layers that you see here, the several different layers as we move towards the top, are still in the same position as they were originally deposited, that is, in horizontal layers. Relative dating principle number 3 looks at the law of cross-cutting relationships. The law of cross-cutting relationships states that an igneous rock or geologic feature is younger than the rocks it has intruded or it cuts across. Two examples of cross-cutting are seen in this diagram. We can look at faults, and in the diagram we see a crack or a black line that moves in the upward and left direction. This crack cuts across rock layers A, rock layer B, rock layer C, and rock layer D. Therefore, according to the law of cross-cutting, the fault itself must be younger than the corresponding layers it cuts across, that is, rock layers A, B, C, and D. Also in this diagram, we see what's called an igneous dike, and that is an igneous rock unit that cuts across other rock layers. So if we look at the igneous dike, here representing gray, it cuts across rock layers A, rock layers B, and rock layer C. So therefore it must be younger than the rocks it cuts across. Also, if we look at the fault in comparison to the igneous dike, we notice that the fault cuts and separates the igneous dike. Therefore, the fault must be younger than the igneous dike. Let's look at rock relative dating principle number 4, the law of included fragments. The law of included fragments states that pieces of one rock found in another must be older than the rock in which they are found in. In this case, we see rock fragments from rock unit D is included in the layer E above it. So if we go over to the diagram, we see that fragments of layer D below, when it got eroded or it got layer E above it formed, rock fragments from layer D is included in rock layer E. Therefore, because they are included in rock layer E, therefore the fragments must be older than the layer that it's included in. So in conclusion, the law of included fragments would state that all of the rock fragments that you see in layer E must be older than the layer E itself. The fifth dating principle that is used to arrange geologic events in relative dating or relative age is unconformities. Unconformities are buried erosional surfaces which represent gaps in geologic time. Unconformities form when land above sea level is eroded and sinks. Sediment is then deposited over the eroded surface and buries the erosional surface. These buried erosional surfaces can exist in 3 different types of unconformities, and they include number 1, an angular unconformity, number 2, a disconformity, number 3, a nonconformity. Information on unconformities can be seen in the text on pages 222 and 223. Let us have a little closer look at the different types of unconformities. When you look at an angular unconformity, an angular unconformity is caused by compressional forces which cause layers to fold and uplift. That means the ground is basically folded into upfolds and the ground rises up. These folded layers are eroded and later sink, where sediment buries the erosional surface. And lastly, the rock layers below the erosional surface are inclined and intersect rock layers above at an angle. If we refer to the diagram below, we will notice that we have several rock layers. And all of these rock layers are actually eroded at an angle. So if we look at the rock layers themselves, they are inclined at an angle, which is due to compressional forces coming in from the sides, which ends up in the sedimentary layers being folded upwards. At a later time, erosional forces will cause these inclined layers to be worn away. This erosional surface is what we call a nonconformity. Later in time, all of the eroded surfaces are then buried when they sink below sea level. Let's have a look at the second type of unconformity. This one is called a disconformity. A disconformity forms when rock layers above and below the erosion surface are arranged horizontally. In the sequence of diagrams to the right, we see that we have a series of layers of sediment being deposited beneath water level. That could be an ocean or a lake. Once this area gets uplifted, the lake will drain, and the surface then is exposed to erosion. Once the surface gets eroded, we see that we have an eroded surface all the way along the top of this layer. Later in geologic time, these layers will sink below the ocean level, where again we see sediment being deposited on top of the erosional surface. Therefore, this erosional surface, which has layers above and below, both horizontal to the erosion surface, is called a disconformity. So in conclusion, a disconformity, you will see that the layers below the erosion surface and the layers above the erosion surface are both horizontal. And this type of unconformity is called a disconformity. The third type of unconformity is called a nonconformity. A nonconformity is an eroded surface of metamorphic or plutonic igneous rocks that are buried by younger sedimentary rocks. So again, in the diagrams to the right, we see in the lower diagram we have an intrusion of magma which forces its way up through Earth's surface. Once this magma intrudes up through and it don't quite make it to the surface before it cools, it'll form solid igneous rock, which we call plutonic rock. Later in geologic time, this area will get uplifted, where the surface then is exposed to erosion. All the sedimentary layers that existed on top of the igneous rock, plutonic rock, will become eroded right down to the surface of the igneous rock, which we see in this diagram. Next, this geologic environment will again be subducted, and it will be buried beneath an ocean by layers of sedimentary rock. So we see the surface of the erosion that's now buried by layers of sediment, and the rock beneath is here, in this case, would be an igneous rock. The nonconformity could also occur if the rock below the erosional surface was metamorphic rock. So in conclusion, a nonconformity forms when igneous rocks or metamorphic rocks are uplifted and eroded, which then later becomes buried, sinks, and gets buried by sediment layers, and the corresponding erosion surface is buried by sedimentary layers, and this type of unconformity would be called a nonconformity. If you look at the diagram to the right, which is seen on page 22 in your textbook, we see evidence of all three types of unconformities. First of all, a disconformity forms when you have an erosion surface represented here by the red line, and the layers below the erosion surface are horizontal, and the layers above the erosion surface are horizontal. These two erosion surfaces in this diagram are called disconformities. An angular unconformity occurs when you have layers of sediment that are below the erosion surface, represented right here by the red line, and these layers are inclined at an angle, where they are cut off by erosion and then further buried by horizontal layers of sediment. So this erosion surface here is termed an angular unconformity. And the third nonconformity seen in this diagram is seen where we have igneous rocks, which has crystallized beneath the Earth's surface and at a later time was uplifted and eroded. And we also have metamorphic rock that surrounds the igneous intrusion, represented by the wavy lines, which is a characteristic of folding within igneous or within metamorphic rocks. They are eroded. So the erosional surface, represented by the red line here, above the metamorphic rock and the igneous rock, is termed a nonconformity. So if we want to discuss the principles of relative dating, we can look at the law of superposition. So in the diagram to the right, we see that rock layers A is older than rock layer B, which is older than rock layer C, and so on. So the law of superposition states that if the rock layers were undisturbed, the rock layers that are located above are younger than all the rock layers below, but are younger than the rock layers above it. The principle of original horizontality in relation to this diagram would state that rock layers A, B, C, D, and E, seeing that they are inclined, they weren't deposited that way originally. Originally, they were deposited in a horizontal manner, and at some later time, the layers must have been inclined by compressional forces. Number 3, the principle of cross-cutting relationships is indicated by rock unit F. Rock unit F cuts up through rock units A, rock unit B, C, D, and E. Therefore, rock unit F must be younger than rock units A, B, C, D, and E. That is concluded because of the law of cross-cutting relationships. The principle of inclusions is demonstrated in rock unit D. Rock unit D has small inclusions of rock unit C within it. Therefore, the inclusions located within rock unit D must be older than rock unit D itself. And the law of superposition would state that rock unit C would be older than rock unit D. And lastly, as discussed in the last couple slides, your unconformities are caused by erosion, and they are represented by buried erosional surface that are buried by sedimentary layers. And in this diagram, we see the red line that cuts across underneath sedimentary layer G, and that would be an angular unconformity, with the exception to right above rock unit F, which rock unit F is an igneous intrusion. Therefore, right above rock unit F would be a nonconformity. Let's look at some examples. Example 1 states, what principles tell us that the fossil brachiopod in the diagram to the right is older than the fossil gastropod, which is located above it in the rock units in the diagram to the right. So the principle of relative dating that we looked at that said rock layers below are older than all the rock layers above and are younger than any rock layers below is the law of superposition. So for example number 1, your answer would be C, the law of superposition. Example number 2 states, which is true about the relative ages of the layers below. Choice A states that layer 2 is younger than layer 1, but older than layer 4. So if we go to the diagram, layer 2 says it's younger than layer 1. But according to the law of superposition, layer 2, which is located below layer 1, must be older. So choice A is incorrect. Let's look at choice B. Choice B says that layer 2 is older than layer 3, but layer 2 is younger than layer 3, but older than layer 1. So if we look at the diagram, we notice that layer 2 is younger than layer 3 because it's located above it, and it is older than layer 1, which is located above it. Therefore, the answer to example 2 would be B. Your turn. Take the time to complete the following questions. Solutions will follow on the following slides. So you can stop your recording now, read the question, and prepare an answer, and then resume the recording when you have your answer finished. Now that you had time to prepare your solution, let's look at the question. The question reads, identify the geologic principle which can be used to distinguish between the ages of rock layers X and rock layers Y. So if we go back to the diagram, we see that rock layer X is an intrusion which cuts up through 1, 2, 3 rock layers. Therefore, according to the law of cross-cutting, rock layer X would be younger than all 3 of the rock layers, including rock layer Y. So the geological principle that could be used to distinguish between the age of rock unit X and rock unit Y would be cross-cutting relationships. So if we look at the answer, it says the law of cross-cutting relationships is used to conclude that rock unit X is younger than rock unit Y. And this is because rock unit X cuts through rock unit Y. If we need to explain our choice, we can use the definition for cross-cutting relationships. And in this case, it says that any rock unit that cuts across another must be younger than the rock it cuts through. And since rock unit X cuts through rock unit Y, it must be younger. So in summary, when determining relative dating, we can use several relative dating principles. These principles include the principle of superposition, which states that rock layers at the bottom of an undisturbed sequence are older than rock units above. We can use the principle of original horizontality, which states that originally when sedimentary layers are laid down, they are always laid down in horizontal positions. So if they are inclined, tilted, or folded by some means, then this must have occurred after the layers were laid down in horizontal positions. Relative dating principle 3 is the principle of cross-cutting relationships, which states that any rock layer that cuts across other rock layers, such as dike A in the diagram, such as fault A in this diagram, or even the dike and the fault on the other side of the diagram, they must be younger than the layers they cut across. The principle of inclusions will state that any igneous rock unit that is found within another layer must be older than the layers they are found within, because they are results of eroded particles that are deposited within the layer when the sedimentary layer is formed. And lastly, unconformities. We see that a nonconformity is a buried erosional surface, and if we look at the layers below, if the layers below the buried eroded surface are inclined at an angle, then it's called an angular unconformity. If you notice that the layers below the eroded buried surface is horizontal, then it's called a disconformity. And if the rock unit's below the layered erosional surface, then if it's metamorphic or igneous in nature, then it's called a nonconformity.